All right. So, hello everyone. We have the great pleasure to have today Dan Pomerleano, who will talk about non-commutative Cartier isomorphism and quantum cohomology. So, thanks for being here, Dan, and please go ahead.
Okay, thank you so much. I should say that the talk that I came up with doesn't really correspond that well to my title in some sense. It's maybe more going to be about P-curvatures and quantum cohomology, but hopefully that's not a huge deal breaker. I just want to say what I'm going to be looking at, and so I'm going to be looking at monotone symplectic manifolds. So by monotone, for me, I mean that the symplectic class is exactly the normalized to be the first Chern class. And I just have a single kind of differential equation, which is given by where the connection matrix is given by quantum multiplication by the first Chern class or the symplectic class. So this is a standard construction you can do for any symplectic manifold, but in the monotone case, it has certain nice properties. So one of those properties is that it really makes sense on polynomially. So in other words, if you consider the quantum product, and what I mean is I'm just sort of expanding it out to be, so this would be the kind of classical part. This would be the part consisting of curves of degree 1, curves of degree 2, expanded out according to the symplectic area. It's really a polynomial differential equation, or so that's what I'll be looking at here, and I want to sort of the motivation for what I want to talk about comes from some work sort of a lot of what I think about is motivated by mirror symmetry, which I know is considered kind of a cult subject, but anyway, it's hopefully this will be convincing that it's sometimes reasonable. So there are some classical theorems in algebraic geometry from the 1960s about monodromies of proper smooth algebraic families over a curve. So if I have a proper algebraic family, I'll define smooth, then as everyone learns, all of the fibers are diffeomorphic, and so it makes sense to you have this Erasmus connection, so it makes sense to consider sort of about every my curve it will be an open curve, but it'll have maybe some complete to a compact curve, and about every missing point that I have, I can consider sort of the local monodromy about that point. So I have my point pi, and I take a small loop, and I look at just the monodromy, and it turns out those monodromies have really very interesting. They're really very special. So, for example, they're quasi-unipotent, meaning the eigenvalues are all roots of unity. If you want to understand their sort of the Jordan blocks of these monodromies, they're bounded in size. So if the fibers are of complex dimension n, then the Jordan blocks of this monodromy operator have size at most n+1, and then so that's sort of a topological point of view, but another important fact about these this local system is it really comes from an algebraic local system. So if I consider algebraic differential forms on my family, then it's a classical theorem that computes the, so I'm considering relative differential forms relative to the base, that computes the cohomologies of the fibers and gives me a vector bundle over an algebraic vector bundle with a connection called the Gauss-Manin connection. And in a sense that I'll say in a second, that this vector bundle has very mild vector bundle with connection has very mild so-called regular singularities. So just to sort of say what that means, if you have a formal meromorphic connection, I'll say that it has regular singularities if it can be gauge transformed into something of the form AQ, where so if this connection matrix can be transformed to have a simple an order one pole about that point, and then the monodromy is just given by exponentiating the residue of that connection matrix. So so sort of my statement before is about the eigenvalues of this residue once you put it in, once you've gauge transformed it into this form. Okay, so going back to this quantum connection, so I'm thinking about some kind of mirror symmetry. So I want to sort of do this kind of thing and under maybe something similar in quantum cohomology. And for quantum connection, in all known cases, the pole, like if you just write down the pole, you look at the equation, you substitute Q equals to 1, a capital Q equals to 1 over Q, so you make a transformation to Q equals infinity, then the connection has a second order pole. And it's not true that if it's possible, of course, that if you have a second order pole, it could be actually secretly regular. That's possible. But in all known cases, the pole at Q equals infinity is irregular. So so the next simplest kind of singularity that you might what you might hope to do is to get a singularity of so-called unramified exponential type, which means that if you do a gauge transformation, it's not quite you can do a gauge transformation to break it up into a direct sum of different pieces where the second order pole is just of the form a complex number on each piece, so different complex numbers times times the q to the minus 2 times the identity, and then the other pieces are regular, and then so this is a regular connection. And then just as before, you can then talk about the monodromy of this regular piece. And so those are called the regularized monodromy of something that can be put into this exponential type, unramified exponential type form. So if the connection is of unramified exponential type, it makes sense to talk about its regularized monodromies. And then the theorem that we proved with Seidel is that so it's actually a little bit less comfortable for me to give this talk than it would have been a few months ago, because we proved this theorem, which we liked quite a bit, and then some students of Paul had some new insights which have kind of shifted the picture a little bit. So so we thought we understood it really well, and then that sort of changed. But now hopefully I'm still talking about it anyways, because I think maybe the story is just more interesting and waiting for further insight. But anyways, so what we proved was that if M is a monotone symplectic manifold, and we assume that it carries what we call a symplectic or smooth anticanonical divisor. So what that means is that we have a symplectic submanifold. So the definition of this is that there's a symplectic submanifold which is Poincare dual to the first Chern class. So, the Poincare dual of D is C1, and so most monotone symplectic manifolds that we know. Sorry. And another key property that we assume is that so if you have a smooth symplectic divisor inside your manifold, it becomes the complement will become such that the complement is because our symplectic class is also C1, so the complement will become exact, and in this case the complement becomes a Liouville, like some kind of completion of a Liouville domain, and what we ask is that it's actually the complement's actually Weinstein. So that's the other condition. But what I was going to say is that so far most examples of monotone symplectic manifolds are actually algebraic Fano varieties. So that restriction is not. If you can find, all of the examples of this that we know come from algebraic geometry, where that condition that the complement be Weinstein is automatically satisfied. And anyways, what we proved is that in this case the singularity has unramified exponential type at q equals infinity, and then furthermore the regularized formal monodromies are at q equals infinity are quasi-unipotent, meaning they have as we said, eigenvalues which are root of unity, just like in the algebrogeometric case. And then so what I'll explain where the picture moved is that then a student of Paul's, Zihong Chen, he looked at what we did and came up with a totally different argument that doesn't actually, well, maybe not exactly totally different. There's a point of common overlap that I'll explain later, but basically a different argument that doesn't require this assumption that D exists. So that's why I'll explain try to summarize what he did in a moment, or maybe towards the end of the talk. I'll mostly talk about what we did. But so where the methods differ between what we did and and this method using quantum Steenrod operations is in this estimate on the Jordan blocks, and that gives a very interesting distinction actually. So if you have a monotone symplectic manifold and you have this smooth anticanonical divisor, then what we prove is that if you have an eigenvalue of the regularized monodromy, which is not 1, then the Jordan block is of size less than what I'm calling the complex dimension. So n, where the symplectic manifold has dimension 2n, and any Jordan block for the eigenvalue 1 is at most the dimension plus 1. And this is sort of, it's not clear whether our method could give dimension m for eigenvalue 1 or not. That's kind of an algebraic question. But so that's what our method proves. And then if one sort of strengthens Chen's method, one gets a completely different bound, which so if you look at the minimal polynomial for quantum multiplication by this C1, then what so you can break that. So if because of the form of the quantum connection, one knows that these in this particular case, the lambda k's that appear here are the eigenvalues of quantum multiplication by Q inverse of C1, the term that appears here. That's sort of a comes out of the theory, and then and then what happens here? So for each eigenvalue, we get a quantum multiplication. One gets a regularized monodromy, and then the size of the Jordan blocks of the of those monodromies in this case are bounded by sort of the largest Jordan block that appears in quantum multiplication. So the exponent that appears in this minimal polynomial. So there's kind of hopefully what I'm saying makes sense. There's sort of two different Jordan block sizes here, but so one is about quantum multiplication and one is about these regularized monodromies that appear in each summand of the connection. And as far as we know, I mean, it's a very interesting question whether you know, one might suspect that maybe this method kind of always dominates the first method, maybe, but there's no obvious relation. So the question would be whether something about whether all the Jordan blocks of quantum multiplication are bounded by the dimension of the symplectic manifold, which is certainly not a known thing. So, but this is in practice, the second bound can sometimes give some very interesting things. For example, if your quantum multiplication were semi-simple, then which is the case for a lot of nice manifolds, then this gives you basically that these monodromies have finite order. So it's a very strong in practical examples. This gives you a very strong constraint. I mean, of course, I guess if there were no rational curves, then that would be the other sort of extreme to semi-simple quantum multiplication. Then certainly the first bound is sharp, basically. So maybe up to this factor of 1. So in that case, this wouldn't maybe tell you anything much new. Okay, so I'm mostly going to talk about this smooth divisor case. Maybe hopefully at the end I'll get to talk about the other thing, about the quantum Steenrod Chen's approach. But so the motivation for how we approached the situation comes again from mirror symmetry. So if it's the case that one starts with a proper algebraic function, which is generally thought to be the mirror of a Fano variety with a smooth anti-canonical hypersurface, then there's a convenient model for the Gauss-Manin connection, which starts with the following complex. So you take the Duram complex and you deform it by adding in basically wedging with D of with the derivative of your function. And then, you know, one thing I should point out is that right away is that this is a very you know, this family, we're not assuming like that it's smooth. So this will have some singular points, potentially also at infinity. But you know, there'll be some finite singular points that I have not removed in this case. And I'm looking at the hypercohomology of this complex, which then carries an endomorphism, which is induced by this operator nabla q. So I'm looking. I take the derivative and then I multiply by just the function. And so because this is I have some singularities in my space. This cohomology will not at all be in any ways finite over Q exactly. So, but if you take the cohomology and restrict it then to Q not equals to 0, then it becomes this connection here. So then one obtains a vector bundle, and the singularity at Q equals infinity is of unramified exponential type. So I'll explain, and the reason this this works. So because I have certain singularities here, I have to it's better to use the language of D modules. So if you start with the Weyl algebra WQ, so this is just the algebra of differential operators in one variable, let's say over C, then a left module over this is called a D module. So and then a D module is holonomic basically if it's finitely generated and it satisfies a certain torsion condition, which says that for every x in your module, there's some non-zero w that annihilates it. So it's kind of like one can think of it as saying the support in some sense is not sort of two-dimensional. Maybe that's a bit vague, but so if you have a holonomic D module, what's nice about these is that away, just like we saw in the previous case, away from finitely many points, there's some function that if I localize by that function, so if I throw out, there's finitely many bad points, and if I localize the module, then I get basically I get a vector bundle with a connection over it. So okay, so if I have, the reason this algebra is convenient to work with is there's a one can think of the Laplace transform, which basically is an automorphism of this Weyl algebra that may be familiar from differential equations. And the interesting thing is that the Weyl algebra is it's sort of so it just by definition it sort of clearly preserves this holonomicity condition, but if I start with something, what's important for us is that if I start with something with regular singularities, including I also need, remember, the missing point at infinity is also allowed, then the Laplace transform will be a vector bundle over C star, so away from Q equals 0 and infinity, and the connection will be it'll have a regular singular point at Q equals 0. It'll be exactly of the form one expects for the quantum connection. So at Q equals 0, one has a regular singular point, and at Q equals infinity, one has one of these unramified exponential type points. So coming back, so Laplace transform takes regular things to these exponential type things. So that's good. So sorry. So if I come back to this page, so what I meant when I said this is a convenient model for the Gauss-Monod connection is that if one throws away the singular fibers here, then what this computes will be the Gauss-Monod connection, but just kind of, but it'll actually be, but really it's Laplace transform. So the Q operator will be the differential operator that corresponds to monodromies in the fibers, and this operator is kind of like the maybe like what one should think of as action by the base coordinate t, um, and so by the theorem of Griffith that we started with at the beginning, Griffiths, Grothendieck, Katz, um, the Laplace transform of nabla Q and Q has regular singularities, and that's what yields this result here, that nabla Q has this form, regular singularity at Q equals 0 and exponential type at Q equals infinity. So this is kind of the story that we try to mimic in symplectic geometry. So okay. So what should play the role? So the question would be, what is the symplectic analog of this construction? What I'll call maybe the Gauss-Manin D module, to distinguish it from the Gauss-Manin vector bundle with connection. And that involves something called deformed symplectic cohomology. So I look at the complement of my manifold M, and I get something which is a priori Liouville. We're assuming it's Weinstein. The Weinstein property plays no role at this stage. And so what we want to do is sort of Q deform. So we're thinking of this as being sort of our maybe differential forms on my Y, and I want to sort of cook up a Q deformation of this that's equivalent, that's sort of analogous to the Q deformation that I wrote down, just twisting by dW. And really, it turns out that if you want to, so if I already had, in my picture, if I go back, I already had the Duram algebraic Duram differential here was already part of the modulo Q structure. So the analog of the algebraic Duram differential is to really look at S1 equivariant symplectic cohomology. So what I really want is a deformation of S1 equivariant symplectic cohomology, but let's maybe just start with the standard version. So let me explain how this might look, what this looks like. So I start with just a usual model for symplectic cohomology, where I imagine I've introduced some nice using the neighborhood of the divisor. I've introduced some nice conical coordinate near the divisor, and I'm looking at Hamiltonians which are approximately of slope W in that canonical coordinate, and then there's sort of a standard way at the cochain level to model, so symplectic cohomology is traditionally thought of as a direct limit of these increasing the slope of the Hamiltonian. The Floer complex is increasing the slope, but here what I want to do is maybe model this on a telescope, which means that I have two copies of the different Floer complexes, and somehow the differential is what computes makes the cohomology compute that has a component which is the continuation maps, and allows us to compute the direct limit as the cohomology. So This is sort of the standard way to do symplectic cohomology at the cochain level. And I want to deform this by counting curves that carry m additional mark points. So they're modeled on the uh, so I'm thinking of my mark points as varying maybe over the symmetric product of a cylinder modulo r, and I want to count. I just want to consider um, allowing points, additional points that pass through the divisor with intersection multiplicity 1. So that, but when I do this, it'll be important that I don't just to make sort of things work out well. I'm not sort of going between my Floer complex and it of slope W and itself, but that I also simultaneously increase the slope. So that's sort of, otherwise, so if I think about these Hamiltonians, they're kind of modeled on a rotation near the divisor. So the Hamiltonians that I'm looking at always have a set of constant periodic orbits along my divisor D. And if I just sort of naively tried to count things like this, but without increasing the slope simultaneously, then I would I would run into all sorts of problems with breaking along those orbits. But if I do this, so meaning my my Floer equation will vary over this symmetric product, and I'll be increasing the slope at the slope will increase by at least m at the output. Then this is going to lead to a good construction. And maybe another thing to say is that when I actually do the differential, I'll weight. So it's a Q. I'm looking at a Q deformation. So as we saw here, I introduced this parameter Q, and my differential. All of these differentials will be weighted by dm. Will be weighted by a power Q to the m. So the complex will sort of look like this. So it'll have some piece that so you'll have, so in my telescope originally I have just these kind of components here, which this is sort of an algebraic component to make things work out. I have my individual Floer differentials which act which don't intersect the divisor at all, and then I have these additional components which what to say? So but going between the different Floer complexes, so this will be Q times something that intersects the divisor once, and then I'll also have sort of diagonal terms, which what they look like are going to be, so here for these differentials I'm looking at these vertical differentials, I'm looking at the symmetric product modulo r. I also can consider the symmetric product without dividing out by translation, and that will give me these sort of cross terms. So originally this will just be, as in the telescope construction, this is just a continuation map, and these are these sort of this, like this arrow here is sort of a deformed version of the continuation map. So it will intersect the divisor once. It'll carry a power of Q, as is sorry, I've sort of obfuscated, but right. So one makes a complex sort of in the most naive way, and it turns out that it actually one can do this. One has to check what happens as things go to the divisor in various ways, but it turns out that one can make this kind of construction. That's this deformed symplectic cohomology of the complement. And our first sort of, well, maybe a starting theorem is that there's actually one can write down an isomorphism between this and the just the symplectic and sort of a topological quantity. So there's an isomorphism between the cohomology of M adjoins Q, and then one has a direct sum of various copies of the cohomology of the divisor, and this deformed symplectic cohomology. And this is sort of going to be a version of the PSS isomorphism, but for this deformed symplectic cohomology. So we don't actually know. So the degrees here, one thing to say is the degrees of this piece are just, so the degrees agree with the cohomological degree. So degrees agree with so Z, in other words, Z, this formal variable Z that I have here, which is just sort of a formal variable, it has degree 0. So with H star of D grading. And so we don't actually, we can't actually completely compute how, so over here there's a natural Q action, but we don't actually really completely understand how Q acts on this summand here. But what we know is that our map that we write down, Z and Q, is there a relation between Z and Q? Right. So so it would be something like Q times Z. So Q times Z is something that we understand. So Z is just thought, like I say, just thought of as a formal variable. It's not even the case that, this might be very bad notational practice, in fact, because it's not really the case that Z times Z is Z squared, for example. But there's no relation. What is true is that if you take Q and look at 1 times Z, so this element in here, then that will be just the first Chern class thought of as an element in here, in that summand. So the multiplication by Q, this is what I was going to say, is eventually, because the degrees here are bounded, this Q variable we're thinking of as having degree 2. Maybe I didn't say that officially, but it has degree 2 in this case. And so eventually, if one looks at this cohomology, multiplication by Q pushes all of the elements in this summand into here. And so if in particular, if you invert Q, then then one gets an isomorphism between what we said is the vector space underlying quantum cohomology and this deformed symplectic cohomology with Q inverted. So right, so this has exactly the property that I was saying before, that if we go back to this Gauss-Mon and D module, we don't really, it's quite complicated over all of Q, but once you invert Q, you get sort of a nice finite dimensional vector bundle. And maybe the motivation, some motivation for this story is, or a different perspective is, work of Borman, Sheridan, and Varl-Gunish, who constructed a spectral sequence from symplectic cohomology with Q adjoined to the cohomology, this cohomology with Q plus minus, the vector space of quantum cohomology. And one obtains a similar, although not obviously the same spectral sequence from this isomorphism because just if one filters by Q, all of the differentials carry positive Q power, so one has a filtration by Q, and the first page of it would be exactly the same as this, although the subsequent differentials we haven't really done a comparison. Maybe it follows. I think it will follow from the this remark here though. So Mohammed El-Alami and Nick Sheridan have taken these ideas and simultaneously with us they proved the same result, but maybe in a very different way. So let me maybe explain how our map is constructed. So okay, so am I working with coefficients and characteristic 0? Right. So that's thanks for the question. That's a very good question. So no, in our story, this has z coefficients. It can have, and yeah, this works over z, this isomorphism here. Whereas in it's true that El-Alami and Sheridan, their work is over in characteristic 0 because they sort of use Marr-Cartan theory as part of their proof, and that whereas we do not actually use. I mean, if one our isomorphism does not require Marr-Cartan theory. So right. On the other hand, one should say that their divisors are allowed to be quite a bit more general than ours in that they allow SNC means simple normal crossings. So yeah. So right. So we have this. So we kind of just try to write down a map between the different things. It's kind of the most, if you want to standard Polarity theory way to do things. So what we do is, so on the so the CM star I'm thinking of is, I mean, you can do it with Morse theory. Maybe to describe the map, it's a little bit easier to think of it in terms of just ordinary pseudocycles. But I want to assume that I have some pseudocycle in M that meets D transversely, and I just look at a thimble, like the ordinary PSS construction, but I just allow so now I'm looking at the symmetric product of the thimble, and I just look at I do the same kind of thing. I just allow my marked points to pass through. I have M additional mark points that pass through the divisor, and they're weighted by some q to the m power, and that gives me like the component of, that's how I define the component of the map on this part, and then on the other part is a bit more complicated maybe. So I have, maybe this is where this dummy variable, this w comes in. So what I do is I look at my thimble. Oh, that's definitely not. I just want to show my face. What I want to do. Okay, this is what I want to do. I look at this thimble, and I instead of the way I take w into account here is I have this mark point, and I put a tangency constraint at w of order. I require my thimble, my thimble to have a tangency of order w at my distinguished point at I guess this would be like infinity of the thimble, CP1 minus infinity, CP1 minus 0, this would be infinity. So at this distinguished point at infinity, I would have a tangency of order W. And then for my other mark points, I have my m additional mark points, and I do the same. As before, I have them pass through the divisor simply. And in total, this gives me a map between this, I guess, you can think of pseudocycles in D or Morse cochains in D to the symplectic cohomology, this deformed symplectic cohomology, and using some kind of filtration arguments, we're able to show that it's actually an isomorphism. Okay, maybe I'll skip. This sort of just says what I said before, that it's really interesting to try to think about what the Q module structure, if one thinks about this map, it's interesting to think about what operations sorry, on the source correspond to multiplication by Q on the target, but it should involve some kind of relative Gromov-Witten invariance, but we haven't really pursued that too hard. But yeah, but sort of the main thing I do have to say is that we can also do this kind of construction S1 equivariantly, and this is the real thing this is the thing that's actually I really need for this story is I also incorporate S1 equivariant cohomology, which you can, there are different models for how one does this. The way that we're thinking of it is sort of by having so this looking at cylinders, but where the cylinders are also decorated with certain angles. So this is sort of the model introduced for this by Ganatra and other people. But if one uses this kind of model for S1 equivariant symplectic cohomology, these angle decorations, then it's very easy to just introduce, as before, additional mark points where the curve intersects the divisor, and that will, so the story that I told with just introducing additional mark points that pass through the divisor generalizes quite straightforwardly to the S1 equivariant theory. But the important point is that when one does Hamiltonian flirt, when one wants to construct connections in Hamiltonian flirt theory, it's sort of well known that one has to use the S1 equivariant theory. So the construction of connections in Hamiltonian flirt theory also works for this deformed symplectic cohomology. So this deformed symplectic cohomology carries a canonical connection nabla Q, and the full sort of Gauss-Mon and D module in symplectic geometry is going to be this Q-deformed S1 equivariant symplectic cohomology with this nabla Q connection. So the theorem is that one can prove is that just as before, it's sort of, again, not so difficult generalization of the previous theorem, is that there's an isomorphism now of this form, which is cohomology adjoins U and Q, and then one has, as before, this part of the divisor, but this part corresponding to tangencies along the divisor. But once you invert Q, those tangency components go away, and what one's left with is just the cohomology of M adjoins U and Q plus minus. And the key property is that we have here is that the connection that I constructed, or maybe there's the connection that after I invert U as well, corresponds to the quantum connection. So under this isomorphism, if I take the connection on deformed symplectic cohomology and I invert Q, I get exactly the quantum connection on M. So that's sort of, you know, the property that I want. I want that I have a kind of a vector bundle over yeah, maybe I didn't even say that U here I'm thinking of as U is the S1 equivariant variable. So it also has degree degree 2. And so if I invert U, that's basically the same thing as, so I have a variable U here, but if I invert it, it's basically the same thing as making my quantum cohomology 2 periodic instead of graded. And the connection corresponds to the connection that I had before. So right. So now I want to say what how we actually, so we have this Gauss-Monod connection. How do we actually prove that it's that it's of exponential type here? So so the basic point here is something that is an argument that is to mimic Katz's approach to proving. So I said Katz had an approach to proving regularity of the Gauss-Monod algebraic local system, and also these Jordan block bounds. And so we want to mimic that in symplectic geometry. So so the way that you do the key invariant here, and this is really important both in our argument and Chen's argument. This is kind of the common features that both use this notion of P-curvature. So it turns out that if one in characteristic P, if one has a derivation in characteristic P, then and one does the pth power of that derivation, that remains a derivation. So if the P curvature takes any sort of derivation, and I plug that into my connection and do the p-fold iterate of that, and then subtract what I get by applying the connection to the p-fold iterate of the derivation. So since we have a very kind of simplified, that's why it's called P curvature, because it measures the difference between these two operations. But in the case of a connection in one variable, it simplifies quite a bit, because the derivation dz itself, if one looks at its p-fold power, that's just the zero derivation. So so in this case, all you're really doing is, if you have a matrix, a connection matrix, is you're just looking at the p-fold iterate of this operator. So it's basically dz plus a to the p. So that gives some matrix depending on over my coefficient field. So right. So we're gonna look at this reduction modulo p, and and what this P curvature over fields of characteristic P, what it allows you to do is it gives a condition for being regular singular. So so if I start with something defined in characteristic 0, so let's say it's defined over a number field. So like that's another important property of the in the Fano case, you know, in everything is defined over Z, in fact, the quantum connection. But in general, I have something over a number field, and then I have a connection there. If it's the case that when I reduce my connection modulo P, I have nilpotent P curvature for all primes, then the original connection, viewed as being defined over the complex numbers, has regular singularities and quasi-unipotent monodromy around each singularity. And in fact, it's really important actually to keep track of so this is my P curvature, the order, like the exponent of nilpotency is very important, because the exponent of nilpotency is what controls the size of these Jordan blocks. So the theorem is that if it's nilpotent of some order mu, then all the Jordan blocks of my monodromy have size at most mu. So that's what we're gonna try to apply. So now here comes the thing that was supposed to be my title, but I definitely didn't have much time to really explain it or delve into it. But anyways, so the idea is what we want to do is sort of so you know what Katz proved is that if one looks at the de Rham cohomology of a family of algebraic varieties in characteristic P, then it has this the P curvature of that connection will be nilpotent. And very recently, so Kaledin and then, well, really Petrov, Vaintrov, Bologodsky, building heavily on work of Kaledin, have generalized Katz's work to the setting of categories, actually. So what they prove is a version of this for so-called smooth. So my original family was smooth and proper over some, in algebraic geometry, it was for families which are smooth and proper varieties over a curve. Here I have some, there's analogous definition of what it means to be a smooth and proper DG algebra or DG category over R. And what they prove is that if one takes the naturally defined connection on, there's a naturally defined connection on periodic cyclic homology of this category, that the P curvature is nilpotent there. So that's sort of the big theorem that we end up wanting to exploit. And in our case, where we apply it is the way that we apply it. Maybe I'll take just a few more minutes to say, if that's okay. So the way we apply it is actually we're looking at the wrapped Fukaya category of the complement, and we're viewing it as being linear over linear over one of these thimble functions. So if I look at the thimble that intersects the divisor once, I get an element of SH 0th degree symplectic cohomology. And so I can, when I have that, I can view the wrapped category as linear over this curve. But it's not actually smooth over this curve. But what we prove is that it becomes smooth in this homological sense after you invert the minimal polynomial of the operator of quantum multiplication. So that's sort of the key theorem. So I mean, work of Ganatra, Pardon, and Shenda it proves that the wrap category, so whatever your ground ring is, it's smooth over that. But here we're actually incorporating this additional variable t. So basically what we want to plug in to Petrov-Vologodsky's theorem is going to be this category, which is linear over this ring. So I think I'm actually out of time, but maybe I'll stop here if there's some questions, or I can explain the last few things I wanted to explain, or I mean, maybe questions will lead in that direction. So thank you.
Thank you very much, Dan. So let's see if your wish will be
well, that's not
satisfied. I mean, let's see what questions we get, or you
yeah,
get,
sure.
rather. So let's see, questions. Okay, there is one question on chat, maybe from Alex Ritter. So maybe you could say a few words about the effect of localizing at F on Wx.
Right. So, okay. So if we go back to the very original setup, here, let's see, where were we? Let's see. Yeah, what the algebraic setup. So it's sort of the analog of throwing. What we have is sort of the analog of this Gauss-Manin D module here, and what we want to do is sort of we get a vector bundle after throwing away the singular fibers. So this localizing by F is the analog of throwing away the singular fibers. So maybe I can say why those are the singular fibers. If one inverts Q here, basically, like, you can, if you look at just the piece of the map that goes from what do I want to say? What your if you invert Q here, your cohomology, like, maybe also throw away the Deformation differential, it will sort of be concentrated to the critical locus of your fibration. Basically, you're kind of computing in some sense, like, at least if you go from n-1 go from dimension n-1 forms to dimension n forms, you're kind of computing the Jacobian. That would be a piece of this differential here. So the cohomology concentrates to the critical locus. So when you pass to Q, when you invert the invert this like the support of quantum cohomology, that's basically like throwing away this part that's not Q torsion, and you're left just with the Q torsion part. That's sort of the idea. So the part that what I'm saying is, if you invert Q, which is the non-Q torsion part, that's concentrated on the singular locus. So if one throws away the quantum cohomology, or the support of this not Q torsion part, everything else is Q torsion, and becomes a vector bundle. That's meant to be the algebrogeometric analog of that. So it's sort of, and there's a homological algebra version of that argument that proves this smoothness, that like once you've inverted this polynomial, everything becomes torsion over Q, and then in there is smooth. So that's part of maybe that's a bit confusing, but I guess maybe the most naive way to say it is it's the analog of the step of passing to the non-singular locus.
All right. So thanks a lot, Dan. So Alex says that he's happy.
Okay.
But okay, are there any other questions? Yes,
Yeah.
Claude,
May
maybe?
I ask a silly question? Are there consequences of your theorem to something like counting rational curves? Does it say something about how the number of curves grows with the degree or anything like that? Is there any?
Yeah, I would really love for that to be the case. Right now, we can't place a constraint on the quantum D module that precludes the non-existence of rational curves. So if one just takes the cohomology without any rational curves, so this C1 multiplication would just be the ordinary cup product. Right now, all the constraints that I've told you, they all apply, unfortunately, to this undeformed.
No, what I mean is, it would rather be the opposite, that the number of curves doesn't grow too fast somehow. Do you get this kind of?
Oh,
If there
okay.
are two curves, then that's satisfied indeed.
Oh, okay. Maybe, yeah, I haven't thought about that sort of direction. Maybe I should think about that instead. I was trying to do the opposite. I was trying to say, could I come up with something that tells me that there has to be a rational curve, which would be, I mean, in the algebraic case, maybe that's not so interesting, but in the general monotone case, that's, I guess, a question people are interested in. So, but yeah, I'll have to, maybe I'll try to think about it, and I don't know the answer, but
Okay. Thanks. Great talk.
oh, thank you.
Okay. I don't know if there are any other questions. We still have a few minutes, Dan. So in case you wanted to say a few more words, you have time.
Maybe there's probably interest in what the other sort of approach that I alluded to, but then conveniently didn't get to. Which is, so what which is this approach of Chen, which is kind of like, for me, was sort of maybe the first time that I thought I understood something well, and then like somebody said something, somebody gave a totally new angle on it. And what he studies, so our thing ultimately, this Petrov-Vologodsky, if it applies to the P-curvature of the Laplace dual connection. But Chen, he does something very similar. So we don't. So the logic is, I'm trying to apply Katz's theorem, and I want to prove nilpotency of P curvatures and get regularity. But since my quantum connection, I don't expect it to be regular. One didn't really think about applying Katz's criterion directly to the quantum connection itself, and that's what Chen actually does. So, and the idea is that if one looks at the P curvature of the quantum connection, multiplied by this variable u, then you can make the following calculations fairly easily. I should say that so basically, if you take q to the p times this P curvature, it behaves like like so up O of u means modulo the ideal generated by u. So modulo the equivariant variable, it behaves like a p-fold quantum multiplication by C1, and then modulo q, it has this form here, and what they both Chen Zihong and his other graduate student Jae-hee Lee, who was maybe the first person to notice the similarity between quantum Steenrod operations, and so these, I don't have time to really say what these are, but these are quantum deformations of the total Steenrod operation. So what Jay and Zihong notice is that like these properties of the P-curvature, if one just calculates the P-curvature, are exactly the same as the as what one gets from the quantum Steenrod operation. So a priori, for a general C, one gets something like this. But if one recalls that if one has a C is of degree 2 and its mod P reduction is it's a mod P reduction of a Z valued class, the Steenrod operation of the total Steenrod operation is just given by this formula, which really resembles this P curvature formula here. So they have exactly sort of the same formal properties, and what there's also maybe here there was an additional property that the P curvature just sort of by definition commutes with the connection, but that's also true for the Steenrod operations due to that's actually a theorem though in that case due to Seidel and Wilkins. And so what this will appear in forthcoming work with Paul with Seidel is that for any P one gets an actual equality of the P curvature with the quantum Steenrod operations. So as I was saying, maybe there are two grad students who are involved with this story more than me, even much more than me. So Jae-hee Lee was the one who kind of noticed the similarity and made some calculations, and then Chen used a weaker version of this statement, which is just that that the difference between quantum Steenrod and P curvature is nilpotent. He used this to give an alternative argument for our this exponential type property. So and because this approach doesn't really use this Laplace transform or deform symplectic cohomology at all, it applies without the assumption of this divisor being there, which is obviously a very good thing. But I don't know what I wanted to do, or what I would like to do, is try to understand how this approach at all relates to this theory of Petrov, Vaintrub, and Vologodsky, this other bound on the P curvature, and so that's sort of what I'm more confused than I was. That's why I say I'm more confused than I was 2 months ago. I'm trying to sort of figure out how the two stories sort of fit together, but I haven't managed yet. So maybe that's the last thing one could say.
All right. Thank you very much, Dan. So I don't know if there are any other questions. Maybe I'll stop the recording.